Good morning, everyone, and thank you for being here. Today I will present our work titled CNNs versus Transformers for Urban Semantic Segmentation, conducted by Carlos Ayala, Gabriel Macías, and Miriam Hernández. We are researchers from the Department of Computer Science at Escuela Politécnica Nacional. In recent years, semantic segmentation has become a fundamental task in computer vision, particularly for urban environments where precise scene understanding is essential. In this talk, I will first introduce the problem context and motivation. Then, I will describe the differences between convolutional neural networks and transformer-based architectures. After that, I will explain the experimental methodology, datasets, and evaluation setup. Finally, I will present the results, discuss the main findings, and conclude with insights and future directions. Let us begin with the motivation behind this research. Let us begin with the urban semantic segmentation refers to the task of assigning a semantic label to every pixel in an image. This task is critical for many real-world applications, including autonomous driving systems, traffic monitoring, robotics, navigation, augmented reality, and smart infrastructure analysis. Unlike image classification, segmentation requires detailed spatial understanding and precise localization. Urban environments are especially challenging because they contain complex scenes with multiple overlapping objects, dynamic elements such as pedestrians and vehicles, and large variations in lighting, weather, and perspective. Historically, convolutional neural networks have been the dominant approach for semantic segmentation. However, the emergence of transformer architectures has introduced a new paradigm that challenges traditional assumptions. This leads to an important question. Should we transition entirely to transformer-based models, or do CNNs still provide advantages? Let us first consider convolutional neural networks. CNNs rely on convolutional filters that operate locally across the image. These filters capture spatial patterns such as edge, textures, and shapes, building hierarchical representations through multiple layers. One of the key strengths of CNNs is their inductive bias toward locality and translation inversion. This makes them highly efficient and capable of learning meaningful representations, even with limited data. Architectures such as UNet, DeepLab, and FCN have demonstrated strong performance in semantic segmentation tasks. However, CNNs also have limitations, because they rely on local receptive fields. Capturing long-range dependencies may require deeper networks or additional mechanisms. Transformers introduce a different approach. Instead of convolutional operations, they use self-attention mechanisms that allow every part of the image to interact with every other part. This enables global context modeling from early layers. In theory, this allows transformers to better understand relationships between distant objects, which may be beneficial in urban scenes where contextual information matters. For example, understanding that a region belongs to a road may depend on recognizing surrounding structures. However, transformers often require larger datasets and higher computational resources. Additionally, training, stability, and efficiency remain important considerations. The main goal of this work is not to propose a new architecture, but rather to conduct a rigorous comparison between CNN-based and transformer-based approaches. Specifically, we aim to answer three key questions. First, how do CNNs and transformers compare in terms of segmentation, accuracy? Second, what are the trade-offs in computational complexity and efficiency? Third, under which conditions does each architecture perform best? By addressing these questions, we aim to provide practical insights for researchers and practitioners, selecting architectures for urban segmentation tasks. Now that we have introduced the objectives of this work, let us move to the datasets and experimental design. The choice of datasets is a critical component when performing comparative studies, because dataset characteristics can strongly influence model performance. In this work, we rely on standardized urban scene datasets that are commonly used in semantic segmentation research. Using benchmark datasets ensures that our results can be compared with previous studies and that our conclusions are grounded within the existing literature. These datasets include high-resolution images captured in real urban environments, with detailed pixel-level annotations covering multiple semantic categories such as roads, sidewalks, vehicles, buildings, pedestrians, vegetation, traffic signs, and other relevant urban objects. One important aspect of urban datasets is the presence of class imbalance. For example, large classes like roads and buildings occupy significant portions of the image, while smaller classes such as pedestrians or traffic lights appear less frequently. This imbalance introduces additional challenges during training and evaluation. Another important characteristic is the diversity of visual conditions. Urban scenes include variations in illumination, weather conditions, camera perspectives, and levels of scene complexity. These factors make segmentation tasks more realistic, but also more challenging. By selecting datasets that capture these variations, we ensure that the comparison between CNNs and transformers reflects real-world performance rather than idealized laboratory conditions. Next, I will describe the preprocessing pipeline and experimental setup, which are essential to guarantee fairness in the comparison. All images were normalized using consistent procedures to standardize input distributions across models. Normalization helps stabilize training and improves convergence. We also applied common data augmentation techniques such as horizontal flipping, scaling, and random cropping. These augmentations help improve generalization by exposing models to a broader variety of spatial configurations. One critical aspect of comparative research is controlling experimental variables. Therefore, we ensured that training and validation splits remained identical across all experiments. This prevents biases caused by different training data. Additionally, we maintained consistent input resolutions whenever possible. Resolution differences can significantly affect performance, especially for transformer architectures that may be sensitive to tokenization strategies. Finally, we implemented standardized evaluation protocols to ensure reproducibility and reliable comparison. To evaluate model performance comprehensively, we used multiple metrics rather than relying on a single indicator. The primary metric is mean intersection over union, or mean. This metric measures the overlap between predicted segmentation masks and ground truth annotations for each class. It is widely used because it balances false positives and false negatives. In addition to mean IOU, we also consider pixel accuracy. While pixel accuracy provides a general measure of correctness, it can be biased toward dominant classes, so it must be interpreted alongside mean IOU. Another important aspect of evaluation is computational efficiency. Therefore, we also examine metrics such as inference time and resource usage. Considering both accuracy and efficiency is crucial because real-world applications often require real-time performance or deployment on resource-constrained hardware. Let us now discuss the CNN-based architectures included in our comparison. CNN models typically follow an encoder-decoder design. The encoder extracts hierarchical features through convolutional layers, progressively reducing spatial resolution while increasing semantic abstraction. The decoder reconstructs spatial resolution, often using upsampling operations, combined with skip connections that preserve fine-grained spatial information. One advantage of CNNs is their strong inductive bias towards spatial locality. This bias enables efficient learning of visual patterns and often results in faster convergence during training. Additionally, CNNs tend to require fewer computational resources compared to transformer models, making them attractive for real-time applications such as autonomous driving. However, CNNs may struggle to capture global context effectively without specialized architectural enhancements. Transformer-based models introduce a fundamentally different approach. Instead of relying on convolutional filters, transformers process images using self-attention mechanisms. Self-attention allows each image region to interact with all other regions, enabling global context modeling from early stages of processing. In semantic segmentation, this can help capture relationships between distant objects and improve understanding of scene structure. However, these benefits come with trade-offs. Transformers typically require more memory and computational power, particularly when processing high-resolution images. Additionally, training transformers may require larger datasets to avoid Therefore, evaluating transformer models requires considering not only accuracy, but also efficiency and scalability. Now I will explain in more detail the specific training configurations used in our experiments, since these parameters play a fundamental role in ensuring a fair and meaningful comparison between CNN-based and transformer-based architectures. First, regarding the input resolution. All models were trained using images resized to a resolution of 512 by 1024 pixels. Maintaining the same input resolution is essential because spatial resolution directly affects segmentation performance. Higher resolutions preserve more spatial detail, but also increase computational costs. By fixing the input resolution across models, we eliminate one potential source of performance variation. Next, The loss function used for training is cross-entropy loss with an ignore index set to 2. Cross-entropy is a standard choice for semantic segmentation because it treats the problem as a pixel-wise classification task. The ignore index allows us to exclude unlabeled or ambiguous pixels from contributing to the loss calculation, which prevents noisy annotations from negatively affecting training. Moving on to the optimization strategy. Both architectures were trained using the ADAM. ADAM-W is widely used in modern deep learning because it combines adaptive learning rate updates with decoupled weight decay regularization. This helps improve generalization and training stability. However, we used different learning rates for CNN and transformer models. For the CNN-based model, the learning rate was set to 3 × 10⁻⁴, with a weight decay of 10⁻⁴. For the transformer-based model, a smaller learning rate of 6 × 10⁻⁵ was used. This difference is intentional because transformer architectures are typically more sensitive to large learning rates. Using a smaller learning rate helps stabilize training and prevents divergence. Now regarding the learning rate scheduling strategy. For CNN models, we used a cosine annealing learning rate schedule with a maximum cycle length of 30 epochs. Cosine annealing gradually reduces the learning rate following a cosine curve, allowing the model to explore the loss landscape early in training and converge more smoothly later. For transformer models, we applied a cosine schedule with an additional warm-up phase covering 10% of the training steps. The warm-up phase starts training with a very small learning rate and gradually increases it. This is particularly important for transformers because it prevents unstable updates during the initial stages of training. Next, both models were trained for a total of 30 epochs. Keeping the number of epochs consistent ensures that each architecture receives comparable exposure to the training data. Finally, regarding batch size, the CNN model used a batch size of 4, while the transformer model used a batch size of 2. This difference arises from hardware constraints, since transformer architectures typically require more memory due to attention computations. Although batch sizes differ slightly, training dynamics were monitored to ensure stable convergence. Overall, these configurations were carefully selected to balance fairness and practical constraints. By controlling optimization strategies, schedules, and training duration, we ensure that performance differences observed in the results primarily reflect architectural characteristics, rather than training setup variations. The goal is to analyze how CNNs and transformer architectures behave when training data is limited, which reflects realistic scenarios where annotated urban datasets are expensive to obtain. To do this, we trained models using different fractions of the data, progressively reducing the amount of available training data. To ensure fairness, subset membership was fixed across architecture families. This means that both CNN and transformer models were trained using exactly the same samples for each data fraction, avoiding sampling bias. Additionally, each fraction was treated as an independent experiment. Models were trained and validated separately from scratch, allowing us to evaluate how performance scales with data availability. This setup helps us understand differences in data efficiency between CNNs and transformers. Here, we present the quantitative results comparing the CNN-based model, DeepLabV3, and the transformer-based model, SegFormer, under different training data percentages. The table shows two main metrics: mean intersection over union, or MIO, and pixel accuracy. Starting with the low data, regime, at 10% of the training data, we observe that SegFormer achieves a higher MIO compared to the CNN model, indicating better performance when data is scarce. At 25%, both models show similar performance, suggesting that as more data becomes available, the performance gap begins to reduce. However, when moving to 50% and especially 100% of the training data, the CNN model clearly surpasses the transformer in MIU. This suggests that CNN architectures may scale more effectively with increased data in this specific experimental setup. In terms of pixel accuracy, both models achieve similar values across all configurations, indicating that differences between architectures are more evident when analyzing MIO rather than overall pixel correctness. Overall, this table highlights an important finding. Transformers may offer advantages in very low data scenarios, while CNNs remain highly competitive and even superior when sufficient training data is available. Now, this figure provides a visual representation of the results previously shown in the table, allowing us to better understand how performance evolves as the amount of training data increases. On the horizontal axis, we have the percentage of training data used, while the vertical axis shows the best validation, MIOU, achieved by each architecture. The blue line corresponds to the CNN model DeepLabV3, and the orange line represents the transformer-based starting with the low data scenario at 10%. We can clearly see that SegFormer achieves higher performance than the CNN. This confirms what we observed in the table, suggesting that transformer architectures may have an advantage when training data is very limited. However, as we increase the amount of training data, the trend changes. At around 25% of the data, both models reach very similar performance levels. After this point, the CNN begins to improve more rapidly than the transformer. At 50%, and especially at 100% of the data, DeepLabV3 clearly surpasses SegFormer in MIOU, showing stronger scaling behavior as more data becomes available. Another important observation is the slope of the curves. The CNN shows a steeper improvement as data increases, indicating higher gains from additional training samples, while the transformer improves more gradually. This visualization reinforces the main insight from the table. Transformers may be more robust in low data regimes, but CNNs remain highly competitive and can achieve better performance when sufficient data is available. The image compares semantic segmentation results. The ground truth shows the correct pixel-level labels. The CNN DeepLabV3 prediction captures the general structure, but presents more noise and less precise boundaries. The SegFormer prediction produces smoother regions and more consistent segmentation, although some fine details may be lost. This figure shows the efficiency comparison between the CNN baseline and The CNN model has about 39.6 million parameters, while SegFormer uses only 3.7 million, making it roughly 10 times smaller. In addition, SegFormer reduces peak RAM usage from 1.35 GB to 0.64 GB, which represents about a 50% reduction in memory consumption. Despite being significantly lighter, SegFormer maintains competitive performance, highlighting that transformer-based architectures can achieve strong results with fewer resources. This makes SegFormer more suitable for efficient training, faster inference, and deployment in environments with limited computational capacity. This slide summarizes the strategic trade-off between CNNs and transformers, depending on the deployment scenario. In clean environments with full training data, the CNN baseline DeepLabV3 is the preferred choice, as it maximizes MIO and produces more stable predictions over large, homogeneous regions. In contrast, for noisy or compressed settings with limited data and memory, SegFormer becomes the better option. It is more robust to corruptions, learns faster in low data regimes, and is significantly lighter, with around 10 fewer parameters, making it suitable for resource-constrained or real-world deployments. Overall, the figure highlights that the optimal architecture is context-dependent. CNNs favor performance under ideal conditions, while SegFormer offers better efficiency and robustness in challenging real-world scenarios. The main conclusion is that a valid comparison between CNNs and transformers requires strict experimental control. Using fixed data splits, identical evaluation metrics, and consistent training protocols ensures that performance differences truly reflect architectural design rather than experimental bias. Regarding data scaling, the results show a clear pattern. CNN-based models achieve higher performance when trained with clean and abundant datasets, while transformer-based approaches like SegFormer demonstrate stronger performance when data is limited, highlighting their better data efficiency. Another key finding is the robustness gap. SegFormer shows significantly higher resilience to image corruptions and noisy conditions, with only around a 17% performance drop compared to approximately 67% for CNN, suggesting an important safety margin for real-world scenarios, such as autonomous driving or video streams. Finally, in terms of efficiency, transformers offer major computational advantages. SegFormer reduces memory usage by about 50% and uses far fewer parameters, making it more suitable for deployment in embedded systems or resource-constrained environments. Before finishing, I hope this work contributes to a clearer understanding of when and why each approach should be used, and helps guide future research toward more reliable and efficient urban scene understanding systems. Thank you very much for your attention and your time. I will be happy to discuss any questions, comments, or ideas you may have.